All right, well, hopefully after yesterday, we're pretty good with exponential functions. We can graph them, we can solve them, we can do all those kinds of things. We're going to switch gears to logarithmic functions today, which is the inverse of exponential functions. So if I need to undo an exponential, a logarithm would do that, and vice versa. Okay? The general idea, and this is really important, this concept here, the definition of a logarithm is if you have y equals log base b of x, the base is important, that is equivalent to b to the y power equals x. And so we're going to use that quite a bit to solve some of these equations and to rewrite some of these expressions. Okay? So, example one, we're supposed to write each equation in words, then in exponential form. So, in words, you know, this is log base 2 of 8 equals 3. In exponential, the base of 2 raised to the third power equals 8. That's what that previous page was telling us, okay? So this one, if they just give you log and there's no base, that is a common log and that is always base 10, okay? So if there's nothing written there, it's base 10. So this would be 10 to the first power equals 10, okay? ln, that stands for natural log. That is log base e. Okay, we talked about e in the last presentation. So if this is base e, then I have e to the 0 power equals 1. All right. And this last one, base 3, so this is 3 to the negative 2 power equals 1/9. So those are equivalent, you guys. On the test, if it asks you to rewrite it using exponential, that is what I'm looking for. All right. All right, example 2, write each equation in words, then logarithmic form. So in words, 10 to the third power equals 1,000. So logarithmic, okay, 10 to the third, so it's base 10 to the third power equals 1,000. Okay, I didn't put a base on here because the common log is base 10. All right, this one, the base on this exponent is 2 to the negative first power equals 1/2. Okay? This one, log base e, that's a natural log, base e, to the second power is about 7.389. That would be a logarithmic version of that. This one, the base on that exponent is 9, so 9 to the 3/2 power equals 27. So that's what you're going to end up doing. That's just doing the reverse of what we were doing on the previous screen. All right, determine the value of each logarithm without using a calculator. So we have to know that rule. So what this is saying here, you guys, is 2 to some power equals 8. Okay, and we shouldn't need a calculator for that. We should know that 2 to the third is 8. So that's equivalent to 3. If you went into your math menu on your calculator and you scroll down to log base, you could type it in just like that and see what you get. Okay, so this means 5 to some power equals 1/25. Okay, now I know that 5 to the second is 25, but since that 25 is in the denominator, that's going to be to the negative 2 power. Okay? So, what about this one? This means e to some power equals e. Kind of makes sense though, right? So if the base on your logarithm is the same as the value there, they kind of cancel each other out. E to the first is just e. Okay? Remember this one is base 10, so I've got 10 to some power equals the square root of 10, okay? Well, that square root of 10, when you have a root like that, it could be considered 10 to the 1/2 power, so x is 1/2, okay? So that would be the solution for each of those. Use a calculator to evaluate each logarithmic expression. Okay, You guys shouldn't have too many issues with this. This is literally just grabbing the calculator. On the left column, there's a log button for that first one, log of 1857. I'll go to 3 decimal places, so I get 3.269. Then log of 0.258. I get negative 0.588. And ln, which is just below the log button, 3.592, that's 1.279. And those are strictly calculator ones, guys. If you see that on the test, you're like, all right, I should be able to do this one. Just throw it into the calculator, no problem. All right. So a couple of things about a logarithm. It's always 1-to-1, meaning it passes the horizontal line test. The domain, and this is the opposite, they're inverses of exponentials. So the domain is 0 to infinity. That was the range for our exponential functions. And the range is all real numbers, which was the domain for our exponential, okay? It's increasing if your base is greater than 1, decreasing if it's between 0 and 1. This time the asymptote is vertical, so in general, if I were to graph a logarithmic function, that's going to look something like that. It's actually maybe a little bit flatter up here, but you get the idea. And you can put that in your calculator, just graph log of x to get a good idea of what's going on. But keep in mind that we have that vertical asymptote there, so you have to put that in on a test. Okay, so graph this using transformation. So our vertical asymptote is typically at 0, but we moved everything 3 to the right. So that puts our vertical asymptote over at 3. And we are moving 1 up, but I think that's okay. One thing you can do here, you guys, if you're looking for a way to graph this a little bit easier, you can put this in your calculator and go to your table, okay? But one thing you can do is solve for x here. So I'm going to subtract 1. And I'm going to rewrite it as an exponential. So 2 to the y minus 1 power equals x minus 3. I'm going to add 3. And then if I were to make a table, normally I pick my x values and then generate a y. But here I'm going to pick some y values, and that should generate some x's, okay? I know that I've got to be to the right of this, so I should be getting numbers bigger than 3 for x. So, for instance, if I put in a 1 for y, 2 to the 0 is 1, 1 plus 3 is 4. So when I put in a 4, I should get a 1, okay? Right here. If I put in a 2 for y, okay? 2 minus 1 is 1. 2 to the first power is 2, plus 3 is 5. So 5, 2 is a point on our graph. Well, let's put a, let's see, I want to raise, what did I put in there? Put in a 5. I put in a 2. Let's put in a 3, one more time here. So 3 minus 1 is 2, 2 to the second is 4, 4 plus 3 is 7. So 6, 7, 3. So we're kind of getting the idea of how flat it is. I know it's going to approach that asymptote, so then we get a nice graph of what's going on there. So that's one way to help you. Obviously, if you put this into your y equals, you guys, you can use that log base feature in your math menu. You can go to your table and plot enough points. Make sure that your asymptote's in the right spot though, okay? The calculator does a very poor job of this. The calculator will look like it cuts it off right about here. You need to make sure that you put that down and continue it down towards negative infinity and put your arrow on there, okay? Because the calculator does not do that well. All right, determine the domain of each function. If we remember, the domain in general of a logarithmic function was that x was greater than 0. We had an asymptote there, so we couldn't go left of it. So what we need to make sure of is what's inside these parentheses is greater than 0. So 2x plus 3 greater than 0. Go ahead and solve, subtract 3 divided by 2. That's what the domain has to be. I can't put any number smaller than that. Okay? What happens here? X squared minus 2x greater than 0. Well, if you think back a chapter, we were solving those quadratic inequalities. So we wanted to find out first where it crossed the x-axis. Okay? So we'll do a little bit of side work here. That factors 2x times x minus 2. So I know it crosses at 0 and 2. Okay, so I can make my sign change chart and put in a 0 and a 2. Because I'm trying to find out where it's bigger than 0, where it's positive. So if I put in a negative 5, let's say, that's going to be 25 plus 10. That's a positive result. Put in a number between 0 and 2, say a 1. 1 minus 2 is a negative number. Put in a number bigger than 2, say 5, and I get 25 minus 10, which is a positive number. So where am I going to be positive? Well, it looks like my domain is going to be negative infinity to 0, and again from 2 to infinity. Okay? Looking at part B, for example, 6 here. All right, part C, we're dealing with rational expressions. And so rational expressions have vertical and horizontal asymptotes. And so I have to be cognizant of where we cross the x-axis. So where are we going to have a 0? That would be at 3. And where are we going to have an asymptote? Because we could change signs there as well. So negative 3. And then I got to figure out where that's going to be positive. So if I put in a negative 5, for instance, that would give me positive number on the top, negative number on the bottom, negative overall. Okay? If I put in a 0, I get 3 over 3, that's a positive number. If I put in a 5, 3 minus 5 is negative over a positive, I get a negative number. Okay? And so the only place where we're positive is between negative 3 and 3. Okay? How are we doing with that one? All right, and then this last one, absolute value is always going to be positive. So no matter what I put in for x, that's going to be positive. That domain is all real numbers. Okay, so it's because of the absolute value that I can do that. Otherwise, I have to make sure that what's inside those parentheses there is greater than 0. All right, so before I get to example 7, we have to talk a little bit, and I'll write this off on the sideboard here too. But the magnitude of an earthquake is equal to the log of I over I naught, meaning relatively no intensity, okay? So using that idea, we're going to do some solving with magnitudes and earthquakes here. So find the magnitude of the earthquakes rounded to tenths with intensities given. So Eureka earthquake, January 9, 2010, near Humboldt County, California, had an intensity of 3,162,000 I sub 0. Okay, so if I take this formula, then my magnitude evaluated at I, being this one, is going to be the log of 3,162,000 I sub naught over I sub naught. Okay? Well, this is a calculator problem, you guys. First of all, these I zeros cancel. So I'm going to type in log of 3,162,000, and I get 6.5. So that earthquake had a magnitude of 6.5. So when you hear Richter scale values, they say 6.5 on the Richter scale. That's that value. Okay. The second one, 1,995,000,000 times the nominal intensity. It's going to be the same formula, you guys. I'm just going to be typing in the log of this. So log 1,995,000,000. This time I get a 9.3 on the Richter scale. Okay, and these are powers of 10, so these are powers of magnitude, you guys. So 3 million versus 1 almost 2 billion, that's a big difference in intensity. Even though it looks like, oh, we're only 3 different on the Richter scale, it's really big in terms of the difference in intensity there, you guys, okay? How many times more intense than the reference intensity was the Peruvian earthquake with a magnitude of 8.4? Well, this time I know the magnitude. Okay, and so I need to solve for I naught there, or get something times I naught. So I'm going to rewrite this as an exponential. So common log is base 10, so I can go 10 to the 8.4 equals I over I0. Okay, so I type into my calculator 10 to the 8.4 power, and then I'm going to multiply by I naught. So I get I equals roughly, okay, 251,188,632 times as intense as I sub 0. Okay, so again, just doing some math on the calculator, we had to realize this was base 10, and then 10 to that power equals that. That was our definition of a logarithm from before. Okay, the 1906 earthquake that leveled much of San Francisco had a magnitude of 8.1. How many times more intense was the Japanese earthquake that had one of 9? Okay, so this one, 8.1 equals the log of I over I naught. Okay, so again, I'm going to just do what I did in the last screen. So I'm going to take 10 to the 8.1 power. And this intensity is 1, 2, 5, 8, 9, 2, 5, 4, 1. Okay? And over here, this 9 on the Richter scale okay, same thing, I'm going to take 10 to the 9th power, okay, which is 1 billion, of course. Okay, and what I need to do is find out how many times more. So I'm going to take that 1 billion and I'm going to divide it by this 10 to the 8.1 value, and I get almost 8 times as much, 7.94. Okay, so even though they were only 0.9 difference in terms of magnitude, that's almost 8 times more intense, okay? All right, altitude, temperature, and barometric pressure. Okay, so if you're given this formula, the height is 30 times the temperature in degrees Celsius, plus 8,000, times the natural log of the barometric pressure at sea level, or 76, divided by the pressure in centimeters of mercury. So let's write this one off on the sideboard here. So H, which is our altitude in meters, is going to be 30T plus 8,000 ln P sub 0 over P. And so we're just going to be using this formula again, kind of like the magnitude formula, to solve some problems. So hikers at the summit of Mount Shasta in Northern California take a pressure reading of 45.1 centimeters of mercury at a temperature of 9 degrees Celsius. How high is Mount Shasta? Okay, well, according to our formula, the height is going to be 30 times 9 plus 8,000 times the ln of, oops, okay, P sub 0, which is like that set, what was it, 76, you guys? Let's go back and look. 76 over 40, where are we here, 45.1. Okay, once you get all the numbers in the right spot, this is a calculator problem. So 30 times 9 plus 8,000 in parentheses times the ln of 76 over 45.1. Okay, I get 4,315.7 meters. Double check that that's what the book gets. They say 4316, about the same. Okay, so we're just putting numbers into the right spot, you guys, all right? And I think we're gonna, no, let's do one more here. Market research has shown that Music Master subscriptions, a new service for downloading and playing music, can be approximated by that equation, okay? Where S of D is the number of subscriptions. What sales volume is expected if the advertising budget is $40,000, okay? Okay, and so I think these are in thousands of dollars. The budget is D there, okay? So I think all they're asking me to do, this is a graph of that function, you guys. All I'm asked to do is put in a 40, 2,500 plus 250 ln of 40, okay? I get 3422. Again, I typed in 2,500 plus 250 ln of 40, and I got about 3,422 subscriptions, all right? Now, if the company needs 3,500 subscriptions, how much should be spent on advertisements? So now I gotta go backwards and solve here. So let's put this up here. So I'm gonna go 3,500 equals 2,500 plus 250 ln D, okay? And so 3,500 minus 2,500 is 1,000. Divide by 250, okay? And then if I rewrite this as an exponential, this is base E, so E to the fourth has to equal D, okay? So I get E to the fourth power to be 54, okay? I actually get 5, 4, and since it's in thousands, 5, 4, I'll go 598. I think the book says $54,600, but that's how much money would need to be spent on advertising in order to get 3,500 subscriptions. Okay? All right. Now, I've changed this in the book as well, but we're going to go every other odd on that assignment, guys. So make sure that you're doing every fourth one. So you got about 25 problems to do or so. Again, if you have questions, office hours from 11 to 11:30 each day on Google Meet. All right, good luck.